Okay, so what is relativity? So we can think of relativity as more of an idea or concept rather than an absolute description. So if you think about it, how would you define some form of coordinate system for the entire universe? You could originally think to base it around a grid over your local area, right? And originally that seems like a pretty good idea until you realize that it doesn't encompass the whole universe. And the Earth is spherical, so that doesn't entirely work. So instead, how about you would have the Earth in the center, then you have a coordinate grid based off that. But again, that doesn't work because we know that the Earth orbits around the sun. So instead how about we have the sun with the Earth in orbit around it, and then we center a coordinate grid off that. But again, that doesn't work because the sun is part of the Milky Way. The sun, I don't want to say orbits because that isn't the right word. The sun moves around the center of the Milky Way. So instead, how about we base it off the supermassive black hole in the middle of the Milky Way? Now, at this point, you probably see where this is going. But, expert drawing right here. Best galaxy you've ever seen. But then again, the Milky Way is still moving through space at around about 60,000 kilometers per hour. So, again, that doesn't work. And what relativity tells us is that there is no absolute position of which you can measure velocity. There's only relative velocity, hence relativity. So, for the purposes of this, I'm going to assume that you're an inertial observer in orbit around Earth. Now, what you mean by inertial observer is actually a whole topic in and of itself, but the way Einstein would have defined it is an inertial observer is an observer, better than real life drawings. It's an observer that is that's not accelerating and is moving through space either at rest or at a constant rate, right? But a common misconception is that if you're in orbit, you're not an inertial observer because you're being accelerated towards the ground by the force of gravity. Well, Einstein had a different idea because let's think about this. What is an orbit? An orbit is falling around a planet. So let's say this is Earth and this is you in your rocket. Most realistic rocket ever, it would totally take off. This is you in your rocket. Now, if you want to be in orbit, you're going to be falling towards Earth, right? But you're going to want to have a constant velocity, assuming your orbit's a circle. You're going to want to have a constant velocity perpendicular to that attraction there. So you're not going to be accelerating in this direction. But in order to keep you in orbit, most people think you're accelerating in this direction. But in this direction, you're falling towards the center of the planet. Now let's have a look at a man. Now these are better than pictures, I swear. Let's have a look at a man that's standing on Earth. Now, one way you can think of it is that Earth is accelerating that man down at 9.8 meters per second squared. That's a 2. Second squared. Right. Another way you could think about it is, imagine you're on a rocket with a booster with all these booster particles zooming down, right? And that booster is launching you up at 9.8 meters per second squared, right? Then any man on here wouldn't be able to tell the difference between being on that rocket, zooming at 9.8 meters per second squared, or 1g, or being on Earth. So Einstein concluded that they must be in the same what's called frame of reference, which is they're both accelerating up at a rate of 9.8 meters per second squared. Now, assuming that, let's say you fell off a roof. Right, so there's your roof, there's your house, and there's your man. Right, and then you fell off. Yeah. So now you're falling. You're not experiencing any G's. You're going 0 G. And from your point of view, the whole world is accelerating upwards at 9.8 meters per second squared. Right? So, from this we conclude that from our orbit example, so there's your rocket. The only acceleration is going to be happening down towards your planet, because this is going to be remaining constant. This is your constant velocity. So the only acceleration is going to be falling towards the planet. But we've just concluded that falling towards a planet will be an inertial reference frame. So therefore, the rocket falling towards Earth is the rocket in orbit is an inertial reference frame. Now, Einstein thought of an experiment where he concluded that different people moving at different rates relative to each other, different observers moving at different rates relative to each other, would be experiencing time differently, which is known as special relativity. Now, a derivation for this is, I don't want to say simple, but it's a lot easier than you would first think. So, this is based off of some equations by Maxwell that state that the speed of light is constant no matter how fast you're going. Doesn't matter if you're traveling 99% of the speed of light. If you shone a flashlight, it will be traveling 1% the speed of light away from you. It will be traveling the full speed of light away from you. The 299, I forgot the number, 299 million meters per second. So using that, Einstein concluded that if you imagine you had a light clock, right? So a clock that had two mirrors and that shone a light beam between the two mirrors, right? So light beam would shoot there, then back, then there, then back, then there, then back. Right? So assuming you're moving at the same rate the mirrors are, because the speed of light is constant, then from your point of view, let's say this is 1 unit of time. 1 unit of time. Right? So from your point of view, this clock will be running at 1 unit of time. Right? But let's say there's someone else who's moving a bit faster than you. So that, I say a bit faster, it's very, very faster than you. So then, this is your light clock. The light starts off its journey here. Right? But because it will be moving down from the perspective of the inertial observer, it will be moving down and along from the perspective of an observer that's moving at a different rate. So it'll look like that. And then by the time the lights hit the bottom, this mirror has moved over here, hasn't it? Then it bounces up, and then this mirror has moved all the way here. Because it's at a constant rate of acceleration. Now, let's think about this real quick. This is going to be your 1 unit time. And this length here, 1 unit time over the speed of light. Because we're using the speed of light as our calibration speed here. Then this length here is going to be how far you've travelled in 1 unit of time. Now, if you remember from high school, speed is distance over time, and then therefore distance is speed times time. So the distance it will have travelled will be the speed at which it's going, which we'll call s, times the time it'll take the clock to go, so that's 1 unit. And then using those rules, a bit of Pythagoras and some simplifying, Einstein showed that the rate you experience time differently is going to be the speed of light. I've been writing it the wrong way. The speed of light, which equals c, divided by the square root of 1 take away the velocity squared over the speed of light squared. Yeah. Now, if we plot this, right, so imagine this is our x, this is our y, at this point we have c, and we'll only plot this way forward because we're assuming that your velocity can't be negative, which I think is a pretty good assumption. Now, it starts really slowly, then right at the speed of light, it shoots off all the way to infinity. Right, so at any normal speed, which are still going to be really close to the origin here, no one's going to notice it, which makes sense because Einstein was simply improving on Newton's ideas. And at Newton's time, no one would be travelling anywhere this close to the speed of light. Anything on horseback and stuff, Newton's laws would still apply in full force. No pun intended. But as you get closer and closer to the speed of light, imagine this is an asymptote, going from the speed of light all the way down. As you get closer and closer to the speed of light, if we have a look at our equation, 1 over the square root, 1 take away v squared over c squared. Now, if we think about this, as v gets closer and closer to the speed of light, v squared gets closer and closer to the speed of light squared, which means this term gets closer and closer to 1, doesn't it? So then we have 1 over the square root of 1 minus 1. But then this is going to equal 0. So we have 1 over 0, which means that at the speed of light, it's undefined. Because 1 divided by 0 has no absolute answer. Has no answer. And then there's special relativity. General relativity, sorry. And general relativity is a lot harder to get your head around. And the derivation of the equations are way harder than my two brain cells can understand. But if we think about them in a logical sense, then we know that then Einstein worked out that you had a spatial dimension. So in the 3 spatial dimensions, in this case I'll use 1, make it simpler. And then I'll use 2, sorry. I have a spatial dimension and you had a time dimension, which you can think of it as going up and down. Now, because I'm using a 2-dimensional blackboard, if you have a 3-dimensional blackboard, link in the comments. But because I'm using a 2-dimensional blackboard, you can't really see it, so I'll be drawing a cross-section here as well. Alright, now let's say we put a star right in the middle here. What Einstein showed was that the star would cause a little dip, just a little dip, in a space-time like that. Now, technically, because of Newton's equations, that little dip will spread out to the farthest reaches of the universe, right? The whole universe will dip a little bit. But because the gravity will decrease, the gravity is inversely proportional to the radius squared, to the distance between the two objects squared. That gets really small really fast, which means that within a few light years, it's basically negligible, right? Unless you have a really massive object. And then Einstein reasoned that if you were staying still in one of these spots, because technically you'd be falling, technically your inertial reference frame would be falling towards the center. If you were in that spot, then staying there, then you'll be accelerating at the same rate you're falling. And then because of that, then you'd be experiencing the time dilation, because you'd be moving at a different rate than an inertial observer. Now, what are the applications for relativity? Because it's all well and good having an idea that describes how things move in the universe. But Newton had these ideas much before Einstein, and they've been holding out for many hundreds of years at this point. Well, Newton's laws do hold out for basically anything that people want to do. But if you want a true understanding of the universe, then relativity needs to take over. And a classic example of this, on the left hand of the story, is, let's say you're on Earth, and you're during an eclipse, right? Now, because of the curvature of space-time, Einstein could show that light would be altered. It would move relative to a high gravitational body. Right? This is the sun here. Imagine this is an eclipse happening right now. Yeah, so the light would move relative to a large gravitational body. Now, last I checked, there weren't any black holes in the area, especially not on Earth. A good thing there aren't. But the largest gravitational body, which is close enough to us for us to do something with, is the sun. But quite annoyingly, the sun's pretty bright. Now, that's all well and good for if you want to be alive, but that makes it a lot harder to do experiments with the light that not coming from the sun but very close to the sun. Now, luckily for us, we have a moon, which is apparent size is roughly the size of the sun, so it blocks out most of its light. So let's say we have some distant star over here, right? Now that light's on its merry way, then it comes close to the sun, it alters its course, then meets an observer on Earth who's also watching the eclipse. And the observers here, in I think it was 1976, noticed briefly the star briefly flash on, then go off again when the eclipse was over. Now, if you try to predict that with Newton's laws, right? So this is the actual position of the star. This is the sun, moon, Earth. Right. Light changes. I'm overly exaggerating this, by the way. Yeah, the light didn't change the course by this much. According to Newton's laws, this star would have been over here, which meant that it would have about half the gravitational lensing than with Einstein's laws. And then later observations shown basically 6 months later, because if you imagine the star's over here, then the Earth was there when the eclipse happened. Right, this is the star, this is the Earth. When the eclipse happened, this is the sun. Then if you just wait for the Earth to be over here, say this was in June, this will be in December now. This will be in December. Then you'll be able to see the star in the night sky to double check where it is. And when people did that, the amounts were perfectly predicted by Einstein's equations and general relativity. So that's a brief roundup of relativity, Einstein's theory, and yeah. Or how do I stop this? Wait, no, wait, my finger's covered in chalk, wait.